Hi everyone, welcome back to Math 256. This is Scott. Let's get started. There is one missing case that we have not really explored in these little 2x2 systems, and that's the situation of repeated eigenvalues. So that's a case that requires a little bit of special handling, and so let's have a look at that. Section 5.5, which is multiple eigenvalues. Now this is actually a little bit misleading, the title of this section. So multiple here means repeated, as in they have multiplicity. So this means repeated. Repeated eigenvalues. In other words, i.e. have multiplicity. So by multiple, it really actually means single, but anyway. So as an example of something like this, let's take a system that we can represent in a matrix form of, say, x prime, so the vector x prime is equal to, and then we have a matrix 1, 8, -2, and 9. And then times x. So what we will do here is the usual thing. So we have a matrix and we want to find its eigenvalues, its eigenvectors. So we will take a minus lambda I, it's going to be 1 minus lambda, 8, -2, 9 minus lambda. And then we are going to be taking the determinant of that and setting it equal to 0. So 1 minus lambda, 8, -2, 9 minus lambda, determinant equals 0. Solve this for lambda. So we would multiply those and we would subtract the product of those. So it's going to be lambda squared. It's going to be minus 9 lambda minus 1 more lambda for minus 10 lambda. And then we're going to have plus 9. And then we're going to have plus 16 equals 0. So this is now the characteristic equation, and that will then lead us to lambda squared minus 10 lambda plus 25 equals 0, which, sure enough, is going to be a repeated factor of lambda minus 5. So lambda equals 5 multiplicity 2 is what we have by way of eigenvalues. Now, when it comes to eigenvectors, if we want to use this, we can just see what we get. So if we do this, a minus lambda I will be 1 minus 5, so it's going to be -4, 8, we're going to have -2 and 4, which, as we can tell, is not going to give us two distinct eigenvectors that are linearly independent. We're only going to be able to get one eigenvector out of this. So in particular, these two will reduce down, and so it's going to end up being, for example, 1, -2, 0, 0, as far as the reduced row echelon form. And essentially then, if that's what we are talking about here, then x1 minus 2x2 equals 0 is what we'd be looking for in an eigenvector. x1 equals 2x2, which has a solution where x1 is equal to 2 and x2 is equal to 1. The eigenvector here, v, is just equal to 2, 1. But that's the only eigenvector that we can actually produce. Any other eigenvectors will just be linearly dependent on this. So this only has one eigenvector. Well, that's a problem. I should say 1 and then insert here linearly independent. Because any multiple of an eigenvector, any non-zero multiple of an eigenvector is also an eigenvector. But the problem is it's not linearly independent. So we need, in order to get a general solution, more than this. And what we need to do in order to get the other thing is use what is called a generalized eigenvector. So here's the situation. So systems with repeated eigenvalues come in two varieties. So there's the one that we just saw, which is a case where it comes up short in the dimension of its eigenspace, and that's called defective. So fewer distinct eigenvectors than the multiplicity of the eigenvalue. That's what we just saw. This is the usual case. It's only going to be a kind of rare exception that we have one that is not defective or complete. So complete ones, those are what produce the star points. So these have the same number of linearly independent eigenvectors as the multiplicity of the eigenvalue. So if we have a complete system, then actually nothing is changed about our fundamental approach. For complete systems, nothing changes about our fundamental approach to finding the solutions. The approach from section 5.2 works without modification. In particular, the solution that you get is that x is equal to e to the lambda t v1 plus e to the lambda t v2, where these are the two distinct eigenvectors that we were promised by the completeness of the system. So everything goes fine this way, and it's all right. And then the phase portrait will be a star point. So the solutions will form a proper node. In other words, a star point. So all the solutions will point uniformly into or out of the origin, and they'll just make straight lines. Hey everyone, this is me. I just wanted to cut in here and say that in the original version of this video, there was a mistake right here. There was a mistake in the video editing, and so a chunk of the video was missing and a chunk got repeated. So I'm breaking in right now to give you the part that was missing from the original version of this video. So now let's just go over it. So we covered just now the case if the system was complete. Now, if the system is defective, then what we're going to need to do is modify our approach. So if the system is defective, we need to make a slight modification to the approach that we will be employing, and here's the basic idea. So what it's going to rely on are what are called generalized eigenvectors, and here we'll be talking specifically about rank 2. So rank here referring to well, it doesn't matter. We're only going to be talking about rank 2. Okay, so the way a generalized eigenvector works is, so V is a generalized eigenvector of A, which is a matrix and which is associated with the double eigenvalue of lambda if the following is true. So V is a generalized eigenvector of A matrix associated with the double eigenvalue of lambda, so V is associated with lambda, if, on the one hand, it is true that if you take the matrix A minus lambda I, so that's the matrix that we typically use when we take the determinant of that to find the characteristic polynomial, and then we find the null space of this matrix to find the eigenvectors. However, now we're not taking the null space of it, but we're taking the null space of the square of it. So you take the matrix A minus lambda I, you square it, and we're looking for something which times V will equal 0. So A minus lambda I squared times V equals 0 on the one hand, but A minus lambda I times V itself is not equal to 0. So specifically, it is a generalized eigenvector. If it is not an eigenvector, because this would mean, if this were equal to 0, this would mean this was an eigenvector. So it's not an eigenvector, but it is in the null space of A minus lambda I squared. So it is not an eigenvector, but it is in the null space of the squared version. And the square, by the way, here is what makes it rank 2, but since we're just dealing with 2 by 2 matrices, that's the only kind we're going to be talking about. Now, here is a generalized method that we will use that takes into account these generalized eigenvectors for solving defective 2 by 2 systems. So our method for solving defective 2 by 2 systems. So step 1, got to find an eigenvalue. We wouldn't even know that we had a defective 2 by 2 system until we found an eigenvalue and found that it had multiplicity 2, and then perhaps we tried to find 2 linearly independent eigenvectors and fell flat on our face. So we find the eigenvalue, and then we find any generalized eigenvector of rank 2, v2. And in particular, what we mean is something that is not equal to 0, but which satisfies this. Then we set v1 equal to a minus lambda I times v2. And the reason why this would work is then v2, well, we'll discuss why it will work when we actually get into it. So set v1 equal to a minus lambda I times v2. And then this will give us the default format for the solutions, which is going to be different from before. So solutions will now have the format, and the format that the solutions will have is going to look like this. So we're going to have solutions of the format. x1, the vector, is equal to v1 e lambda t. So x1, the vector, equals the vector v1 times e to the lambda t. So nothing new here. This is totally regular. v1, by this construction, is actually going to end up producing an eigenvalue. So v1 will be an eigenvalue. Now it's where the x2, how the x2 is made, that changes things up. So x2 is equal to v1t. So the t here, so this is very similar to what we might have thought we would have to do. We might have thought what you had to do was to do what we have to do in other cases and disambiguate with an extra factor of t. And it's similar to that, but the difference is that we have to do this t times the v1 plus v2, and that times e to the lambda t. So x2 is equal to v1t plus v2 times e to the lambda t. So now, if we expand that out and put in the C1 and C2, which only initial conditions will give us, then we'll have x equals C1 V1 e to the lambda t. So that's going to be the first term, plus C2 V1t plus V2 times e to the lambda t. That'll be the second term. So this will be the general solution here, and then it'll be up to us, based on initial conditions, to fill in the C1 and the C2. So let's try an example of this. So first, let's just try this example right here, where we're going to have x prime is equal to the matrix 1, 8, negative 2, 9 times x. So then, as we already saw in our example, we have at the very beginning of the section, we have a lambda equals 5 with multiplicity 2, and it is defective. Now, find a minus lambda I. So that's the matrix that we would use to find the eigenvectors and such. Now, unlike before, what we are going to do with this, so a minus lambda I equals subtract 5, subtract 5. Okay, so now, unlike before, what we will do with this is we will now square it. A minus lambda I squared, so multiply it by itself. So there it is, being multiplied by itself, and when you do that, you will actually just get 0, 0, 0, 0. So negative 4 times negative 4 is positive 16, minus 16 equals 0. Negative 4 times positive 8 is negative 32. And then plus positive 32 equals 0. Positive 8. Positive 8 minus 8 equals 0. And we have negative 16, positive 16 equals 0. Now, we just need to find any non-eigenvector that satisfies this. So we can tell what the eigenvectors are going to look like here based on this one. We can see that we're going to have an eigenvector. Actually, did we already find the eigenvector? So yeah, eigenvectors will be multiples of the 2, 1 that we found already. So anything that satisfies this can serve as our generalized eigenvector, and notice we have full scope here. We can put anything in there. So we can put in v2 equals 1, 1, for example. So any non-zero v2 can go in there. For example, 1, 1. Okay, so if that is going to be the one that we're going to choose, and we just took that basically out of thin air, then given this, we can find the v1 by doing a minus lambda I times that. So then that's going to give us a v1 of a minus lambda I v2, which in this case is going to be v1 is equal to negative 4, negative 2, 8, 4 times 1, 1. And that v2 could have been anything, but then v1 is going to be dependent on that. So then we would multiply. It's going to be negative 4 plus 8 is 4. Negative 2 plus 4 is going to be 2. And if we compare that with what we found when we started this section, we see that that is indeed an eigenvector because it is double the eigenvector that we found before. And any multiple of an eigenvector will also be an eigenvector. Alright, so then once we have those two pieces, the v1 and the v2, we can boil down the solution into the combinations of the two basic solutions. So c1, e to the 5t. The e to the 5t part can go wherever, doesn't matter. And then times the eigenvector that we found right here. And then plus c2 times e to the 5t. And now here is where the weird stuff happens. So we've got 4, 2 times t plus the v2, which was just 1, 1. And if we wanted to, we could actually rewrite this in its more collapsed form because it makes it a little bit easier to understand. C1 e to the 5t times 4 plus C2 e to the 5t times 4t plus C2 e to the 5t. And then down here be the same things, C1 e to the 5t times 2 plus C2 e to the 5t times 2t plus just C2 e to the 5t. And the important thing about this, as far as noting how these things relate to each other, is that the exponential parts of this are all the same. So it's going to be 4 C1 plus C2 e to the 5t. I'm going to break it down like this. and then for t, c2, e to the 5t. So we've got the part that is not changing and the part that is changing with the t here. And then the same thing is going on down here, where we've got 2 c1 plus c2 e to the 5t, and then plus we've got 2c2, so 2t c2 e to the 5t. Now, the e to the 5t part, as I said, is common to everything, but what is changing about this over time is the effect of these t's. And so what that's going to do is it's going to make the node improper, and then the way it's going to look, so such systems produce improper nodes. And the way it's going to look is that basically this one has a positive eigenvector or eigenvalue, so that means it's going to be a source, and it's going to be, there's only the one eigenvalue or eigenvector in play here, the 4, 2, so that's going to be indicated in this way. And then, so it goes out along V2, or sorry, V1. And then as far as V2 goes, which in this case is just 1, 1, the way that looks is it's not going to be it's not exactly going to be actually I should just write it off this way. It's not exactly going to be involved in this, but what will be happening is that every solution will be basically ending up going the direction of V1. And they're going to be starting off going in the direction more or less of V2. And they're going to get pulled in the direction of the V1. So by the end of the once time gets a little bit big, the solutions all end up parallel to V1 is what's going on. Okay, so that's how those systems look. Let's do one more example, this time of an initial value problem, so we can see how that's going to play out. And then we'll take a look at Old Bluffton to see what it has to say about how these things all end up looking. So that was example A. Now let's do an example B. So this one will be an initial value problem. We'll say x1 prime is equal to x1 plus 2x2. X2 prime is going to equal negative 2x1 plus 5x2. All right, now we have to figure out what the situation is going to be here. So we're going to have a 1, a 2, a negative 2, and I'm sorry, this is x2, not x squared, obviously. If it were squared, then it would not be a linear differential equation, and we'll have to wait until chapter 6 to see what we would do about that. All right, so this is the matrix of the coefficients that we'd get, and then when it comes to finding the eigenvalues, we are interested in a minus lambda I, so that's going to be 1 minus lambda 2, negative 2, 5 minus lambda. And so then when it comes to finding the determinant of this, it's going to be, and setting it equal to 0, it's going to give us That times that is going to be lambda squared minus 5 lambda minus 1 lambda. It's going to be minus 6 lambda plus 5 and then plus 4 because it's going to be minus negative 4. So we have lambda squared minus 6 lambda plus 9 equals 0. In other words, we have lambda minus 3 squared equals 0. So lambda equals 3 multiplicity 2. Oh, and I forgot to mention, I said this was an initial value problem, so we need some initial conditions. x1 of 0 is going to equal 3. x2 of 0 is going to equal 2. So we've got lambda equals 3 with multiplicity 2. Now we can figure out right away once we look at a minus lambda I what the situation is going to be as for whether this is going to be defective or not. So that's going to give us a negative 2, 2, negative 2, 2. Well, since our two rows are exactly the same, it's clear that this is going to be defective, because how am I going to make two different linearly independent eigenvectors out of this? And the defective matrices will be the usual case in this. It will be very uncommon for it to be complete. It essentially has to be almost a multiple of the identity in order for the system of a 2 by 2 to be complete. So that's going to be very uncommon. All right. So here now, let's see what we can do. So we're now actually more interested in a minus lambda I squared than we are even in this. So we just see what happens. So we multiply, matrix multiplication, and we get, looks like 4 minus 4 is 0. Looks like we're going to have, and then we're going to have 4, negative 4 plus 4 is 0. And then over here, we're going to end up with, once again, 0. And then the last one, also 0. This will be a very common case. So V2 can be basically anything we want. Equals 0, V2, and just by default. We just need something that's not going to be an eigenvalue or an eigenvector of this original one. So if my default is to go by like 1, 1, that's not going to work here because 1, 1 would actually satisfy this. So I'll just make it 1, 0. Make it as simple as you can. It's easier. It's easier the simpler it is. You could have also made it 0, 1, just as easy. Okay, so then, if that is our V2, then it's up to us now to find the V1 that we get by multiplying a minus lambda I times that. So that is going to be the negative 2, 2, negative 2, 2 times 1, 0, which is just going to be negative 2, negative 2. So that gives us an x of mystery C1 e to the 3t, 3 being our eigenvalue here, and then times negative 2, negative 2, plus C2, and then here we're going to have e to the 3t again, but now it's going to be the negative 2 times t plus the v2, which is 1, 0. And now we need to find the initial condition, or then we need to find the C1 and the C2 using the initial conditions of x1 0 equals 3, x2 0 equals 2. So x, the vector at 0, will be 3, 2, and that's when t equals 0. So then you just plug that in. So 3, 2 is equal to C1 times, so it's going to be C1, negative 2, negative 2. And then we're also going to have a t of 0, so it's going to be C2. It's going to be a 1. It's 1, 0. And in fact, actually, it looks like you can solve this by any means that you know and love from linear algebra, such as row reducing or what have you. But this is actually quite easy to if we just look at the second line here. So 3 equals negative 2 c1 plus c2, and 2 equals negative 2 c1. So in other words, C1 equals negative 1, which means C2 just equals 1. So then what we've got is a solution of just negative 1 and 1. Negative 1 e to the 3t 2. Negative 2. Sorry, I was already had plans for that negative 1. Plus just 1 times e to the 3t, negative 2, negative 2, t, plus 1, 0. And you can simplify this to your heart's content. Do whatever you like, really. As far as this goes, write it in whatever simplified fashion you wish. But I think what I will do here is I'll just actually spell out what x1 would be and what x2 would be. So x1 would be negative 1 times 2. So 2 e to the 3t minus 2t e to the 3t plus e to the 3t. Interesting. And then x2 is going to be over here, 2e to the 3t minus 2t e to the 3t plus 0. So then what we're going to have is just 3 e to the 3t minus 2t e to the 3t. And over here what we're going to have is 2 e to the 3t minus 2t e to the 3t. And again, there are a wide variety of different types of presentations of the solutions, and you can just go with your heart on those. Now we can also actually we can make a rough sketch of what this is going to look like, and then we can compare what we produce with what is produced by something more professional, such as a Bluffton style applet. So so this is going to be our v1 going that way, and that means the negative v1 pointing out that way. Also an eigenvector. In fact, all the eigenvectors will be the things that point right along this line. And then what's going to be happening here is however any solution curve starts, it ends up eventually pointing in a direction parallel to v1. No matter which way it goes, it always ends up parallel to the V1. So this is an improper nodal source. Hey everyone, I just actually wanted to do a slight correction on this. I just realized I made a slight mistake on this. So it's obviously, so my conclusion is not changing. It is an improper nodal source. But one thing I forgot about here is the fact that this particular direction is the one that it is going to be pulled in as t goes up. So that is not actually, it's almost right, but not quite. So we are going to have still the eigenvectors going along here that that will be pulling. So that'll be pulling solutions away from the origin, and they will all be eventually pointing in the direction of V1, but not the V1, the negative V1, but actually straight up V1. So the negative 2. Negative 2 is the general direction that will overwhelm this one as t gets bigger. So everything is balanced about this except for the fact that this t is pulling it in the direction of that vector. So what that means is whatever direction you start off in, so whatever way you are pointing to start, you are eventually going to be pulled around that way. And that is so that's going to be making like a, it almost looks like a spiral, but it's actually not quite a spiral. It's because everything ends up trying to get parallel to the V1 here. Now on the other hand, if we are over here, then we're going to be getting pulled. We're getting pulled. Actually, it always has like a kind of a spirally look to it, so I guess it's gonna be like that, and then over here like that. I don't know. Something along those lines. It's not really worth it to try to produce the exact nature of these that well, because it is a little bit tricky. But it does. But it is improper. It is a nodal source, and if you want to see a good picture of it, you have to go to something like Bluffton to get an accurate view. So now let's actually get a view of some of the scenarios that can happen with these various things, and we'll use our favorite little Bluffton applet for all of these, for all the graphing purposes. So you just type something like slope field generator, and especially if you've done it before on this particular computer, it comes up pretty fast, and you just scroll down until you find the one from Bluffton. Now here you can have a system. X and Y will be playing the roles of x1 and x2, and so if I went to that system right there, it's going to be x plus 2y, and then here it's going to be negative 2, 5. Negative 2x plus 5y. Alright, and so the system does produce this little it looks like a spiral. Don't be confused though, it's not quite a spiral, and what happens is the things are all just getting generally pulled, whatever their initial direction, they're getting pulled until they are going to be parallel to the V2, and then depending on where they start, if they start on this side, they'll be going towards the regular V2, and if they start on a different side, that would effectively give it a negative value of the C1 C2, which will then be pulling it towards the negative version. So our version, so for our initial conditions, it's over here, which what it's going to be eventually doing is going to be going all the way around, and we may have to zoom out quite a bit to see this, but it's going to be going all the way around and eventually end up parallel to the V1. So I'm just zooming way out here. And let's just clear all of these curves, make it a better plotting system, and we'll make it a 3, 2. And so notice it gets pulled around until it's going parallel to V1. Okay, now while we're at it, we might as well take a look at some of the other scenarios for graphs that we have explored before. So here is another case. This is an example we did in section 5.2, where we had 2x minus y, and then 4x minus 3y. Oops. And this is, so this one is going to be a case of two distinct eigenvectors. And you'll notice that what we have here is a saddle point. We've got some going in, some coming out from the origin. So it gets swept around in a saddle point fashion. Let's see, and then another example was, this one had complex eigenvalues, and what we're going to have is 5x minus 4y, and then over here 5x minus 3y. And so what we've got in this case is a spiral source. So these are the kinds of things that we will be seeing as when we start plotting these different systems of differential equations. But we will be dealing with more of this as the term unfolds. So join me next time for the next episode of Math 256. Until then, bye.